Okay, so I will start with some motivation because I'm not a mathematician, I'm a computer scientist. So I will shortly give you some motivations about this. So in computer science, we have algorithms and some input and some output. And for a given problem, we have several algorithms to solve it, and we want to say this algorithm is better than this one. And in order to say that, we have to actually calculate something to say some measure of the efficiency of the algorithm. So one way to do it is to say, let's fix a size on the input, and let's call IN the input of length n, of size n. And then I have something to that give me the complexity. It can be the amount of time, the amount of space, of energy, whatever you want. So C is a map from, okay, I need also I is all the inputs. And C is a map from I to, say, the non-negative real, which is the cost for a given input. Okay. So in the classical settings, in algorithm, what you are looking at is the sequence which for each integer n, positive integer n, gives you, say, the worst case complexity is you take the max over all inputs of size n of the cost. So this is the worst case complexity. And you can do other things like the average case complexity. So instead you will study something like that. Let's say the expectation, so the sum for all input of size n of some probability measure of IN times the cost for I. Average case. Okay, so my point here is that basically what you have is sequences. This is a sequence of positive real or non-negative real. This is another one, depending on how you define the complexity of your algorithm. But we are dealing with sequences. Of positive reals, non-negative reals. And we want to compare this. So, for instance, one result is, I don't know if you know this algorithm, but quicksort algorithm, which is a very classical one, you can prove that the average number of comparisons you need to sort an array using this algorithm is n hn, where h is the harmonic series. Okay, so this is a result, the expected number of comparisons you have to do to in quicksort algorithm, and for the uniform distribution. And okay, but this is quite complicated, not really complicated, but if you want to compare sequences, you need, for computer scientists, you need something simpler, because if I have to compare it to, say, another algorithm which is in n square, I have to know whether this grows faster or not than n squared. Okay, so the answer is, well, we know that Hn is asymptotically equivalent to log n. So this is roughly n log n. So maybe I should define these notations. So un is asymptotically equivalent to Vn, just means that un equals Vn plus little o of Vn. So n squared is asymptotically bigger than n log n. So this algorithm is better than this one. Okay, so my point here is that for computer scientists, we actually prefer this. There is a 2 here, sorry. This to this. Okay, so we are more interested in asymptotic equivalent than in closed formula. And when you're seeking asymptotic equivalence, you are losing some information. Closed formula are more precise. But maybe in some situations which are very complicated, you have some difficulties to obtain some explicit closed formula, but it's much easier to obtain asymptotic equivalent. So the idea is, can we do some kind of general techniques to directly compute asymptotic equivalence without first computing the closed formula? So this is the motivation. You can interrupt me when you want, okay? Okay. Okay, so let's start for real. Combinatorial set. And generating series. Okay, so to try to say something about the average complexity of algorithms, there are basically two ways. Either you do discrete probabilities, or you are using some kind of combinatorics techniques, and this is what I am going to show you now. Okay. So what is a combinatorial set? It's just a set with a notion of size. So I can write S. E is a set, and S is a size function. Every element has a given size. And what you want is that there are finitely many elements of a given size. So I define En, which is a set of elements of size n, is finite. Okay. So now we are doing combinatorics. We have, for given n, we have a finite set, and we can compute the number of elements, its cardinality, and we are looking at this in this sequence of numbers.
Do you want this function S to satisfy certain axiom, or is it like...
No, it's just the size. Okay, and I will write small en for the cardinality of En. Okay, so now the ordinary generating series so it's quite long to write, so I will just use OGS of ES is the formal power series. E of z. Okay, so I will define it this way. So you take all the elements of the set E, and you have a formal variable z. And you take z to the n every time you get an element of size n. So you can also write this way. This is the sum over all integer of en z to the n. Okay? And the important thing is that it is a formal power series. I don't care about conversions or things like that at this point. And we also have the exponential generating series. This is the same thing, but you divide by a factorial. Okay, so you probably know that very well. This is a very important tool in combinatorics because in a way this is a formal power series, so you don't have done much than, you know, this is a sequence En and you just add some formal variable here. For the moment nothing is done. Now, why do we use this series and not just the sequences? It's just because it's better to define the operation we want to define. So you have two operations, basically. So if I take AZ and BZ to power series, so the sum is simply, so I don't write everything, but so an are the coefficient of A, bn are the coefficient of B. So it's just this one, and to do the products, this is why we use this notation with series, is that you do, I don't know how you call it, but you know the classical product on series or polynomials, which is this one. So at this point, the use of formal power series is just to say that the product of two series is this series, right? Okay, so just quickly, for things to be correctly defined later, I also need to make to use some topology over the ring of formal power series, and because I want to say something like taking the exponential of a power series, and I want to say that this is the sum over all k of a of z to the k over k factorial. Right? But okay, this is well defined because I have a product. I can divide by a number, no problem. But this is a limit. Okay, so there is a limit somewhere, so I have to define it properly. Okay, I will not do everything, but the idea is to say that okay, so the valuation, I don't know if I have to take time on this. It's okay or no? Okay. The valuation of A is the smallest I such that AI is not 0. If the series is just 0, you take infinity. And you say that the distance between two series is, for instance, 2 minus the valuation of the difference. So it means that you converge for this distance when you have more and more coefficients starting from the start that are the same. Okay, so that's my topology. So if you do that, this is well defined. If the first element is equals to 0, because if it is not equal to 0, then you would add some values for each value of k. So the first element will always change, so it does not converge in this sense. Okay. This is not really important, but just to say that you have to. We are speaking about formal power series, not functions yet. Okay, and last thing, I will use this notation for the coefficient, the nth coefficient of A. Okay. Okay, so in classical combinatorics, we use this generating series to say something about the sequences, and the sequences are saying something about the number of objects. For instance, the number of permutations, the number of trees, the number of whatever you want to count. And you can use this tool to classify rational algebraic, things like that. This is not what we are going to do, because we want to do some asymptotic equivalent to these coefficients. But first, in fact, there are two main parts in analytic combinatorics. The first part is to give tools to try to build the generating series directly from the combinatorial specifications. So a permutation is something that you can describe, and you want to directly get the generating series. And the second part is to obtain this asymptotic equivalent. So for the first part, a technique was developed, and it is called the symbolic method. So the idea is that it does not work always. It does not always work. Okay, but when it does, it is very powerful. Okay, so let's start with an example. I want to look at all the words. I will write it in English. The words obtained by concatenating A's and AB's. So for instance, you have this word AB, AB. It's a concatenation of A's and AB's, so it's in W. Okay? Okay, this one is easy if you want to count them. You just, okay, I have the empty word, which is a word of length 0, and I consider it is also in W. So the number of elements of W of length 0 is 1, the empty word. Of length 1, then you have only A, so 1A, so it's 1, sorry. And it's easy to check that Wn is Wn minus 1 plus Wn minus 2, because if you take a word and you add at the end A or AB, there is no ambiguity. And so this is the correct way of counting. So this is a Fibonacci sequence, it is easy. And now if you want to switch to generating series, then you multiply by z to the n, you do some computation, and then you obtain that W of z, equals 1 over y minus z squared. Okay? This means that, this notation means that it is a formal power series such that if I multiply it by 1 minus z squared, I get the identity. Okay? I have to redefine everything if I want to say what exponential is, inverse is, and so on. Okay, so second example. Here. So in computer science, we are using a lot of trees. So a plain binary tree so let's say it's T. And what is it? So it's something like that. Okay. Okay, so you have two kinds of nodes. The circle, which are internal nodes, and the leaves. And every internal node has two children, and the leaves have none. And also, I consider for counting that there is an order between the left and right child, so these two are different. Okay. Okay, so I want to count them, and the size of a tree is the number of internal nodes. Okay, so the first tree is this one, just one leaf. So the size is 0. So we get that T0 equals 1. One tree of size 0. If you have one internal node, then the only possible tree is this one. So T1 equals 1. And if you have two, there are two possibilities, which are this one there. So T2 equals 2, and in fact it's easy to see that Tn, well, you have a root, and then you have something of size k on the left and of size n minus 1 minus k on the right. So it's some okay, I think I made a mistake way before when I defined it the sum. when you take the coefficient of the product, I think I put a binomial coefficient, right? It is not here. Right? I will explain you why I made a confusion after. And nobody reacted, right? Okay. This is a classical product. And the reason is that if you do this product on exponential generating series, then there are some factorial involved, and then you get this binomial coefficient somewhere. That's why I made a confusion. And when I made a mistake, you can yell. Okay. Okay. So here we have this product formula. Okay. So from this, it's easy to see that you get an equation which is this one. This is t of z times t of z, and you take care of this n minus 1 here, and so on. Okay. Okay, so I have two examples, and I want to summarize the example as follows. If you take the set W, what I'm saying is that either you have the empty one, or I will put the union sign. Well, you take an element of W and you concatenate A, or you take an element of W and you concatenate AB, right? And if I do the computation here, what I obtain is that W of Z equals 1 plus W of Z times Z plus W of Z times Z squared. And from this I get that. Okay, so this is example 1. And as for example 2, I will write this informally as follows. A tree is either just a leaf, or maybe I put some bracket here. You have an internal node, and then on the left and on the right you have a tree, right? And the equation here is t of z equals 1 plus z t of z squared. Okay, so there is a pattern here. Okay, so this is a symbolic method. Symbolic method is to say I want to have some combinatorial constructions like the union or some kind of product, Cartesian product, and I want to translate them directly into something on generating series. Right? Yeah. So this is why I spoke about ambiguity, non-ambiguity before. Exactly. So I must be I'm a bit late. So if you take the disjoint union of two combinatorial sets, then of course the cardinality of, I put a dot here to say it's disjoint, is equal to AN plus BN because it's disjoint. And so A of Z, if I say that C is A union B, then C of Z equals the sum of A of Z and B of Z. And okay, so the important thing is for the Cartesian product. So I define C as the Cartesian product of my two sets. So elements of C are pairs of elements of A and B, and so I have to define the size I'm considering before doing something about combinatorics. So I will say that the size of a pair alpha beta equals to the sum of their sizes. So if it is a definition that that's under consideration, then the generating series of C is equal to the product. Okay, so this is nice. This is what we use here, right? Another operation that is really useful is sequences. So I define C as either some, so this is an element of length of size 0, a formal one, or an element of A, or a pair of element of A, and so on. Okay. And if there is no element of size 0 in A, this is well defined. It means that this notion of size that you can extend to A to the K, with this notion of size, C is a combinatorial set. This is not the case if you have something of length of size 0 in A, because you have epsilon, 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 all of size 0, so you don't have finitely many elements of size 0. So if A0 is empty, this is well defined, and C of Z equals, so this is one element of size 0, so its generating series is 1. This is a disjoint union, so this is A. This is also a disjoint union with a pair, and the pair is a product, and so on. Okay. It is well defined for formal power series too, so this is 1 over 1 AZ. Okay. Okay, so the idea of the symbolic method is to give some set construction, and that you can directly translate into something on the generating series. There are more constructions, but I have no time to show you. I want to say some word about the labeled KAIST, which is really important in computer science and very elegant, I think. So now, if you look at the permutation on the element between 1 and n, and you do what is called the functional graph, so the vertices are the element 1n, and you put an edge between I and G when of sigma when sigma of I equals G. And so a permutations looks like something like that. Okay, so you have cycles because it's a permutation. And you see there is something different. We are not exactly in the same kind of things than here, because here I have some numbers in my okay. So this is what I call labeled. So I cannot define everything properly. I don't have the time, but the idea is that you have some atoms which are elements of size 1. The size is the number of atoms. So here you have 6 atoms, and each the atoms are labeled with the element between 1 and n, and exactly 1. You have 1, 2, 3, 4, 5, 6. You don't have, I don't know, 4 twice or something like that. Okay? So this can be defined properly, I just don't have the time. So if you do that, the problem is that the disjoint is okay, no problem, but the Cartesian product, there is a problem. I don't know if you see it. Let's say I have a sequence and I do the pair of the sequence with I don't know, a cycle. Well, it is not properly labeled because I use 1 twice, 2 twice, and so on. Okay, so I have to relabel it. Okay, so I cannot directly do the Cartesian product because I want to handle the labelings. So I will define. So this is a label object. Beta also, and I will define this labeled product as I will we'll write something informal and make an example. I think it's easier. So all the pairs with the shape of alpha beta. By shape I mean if you remove the labels, you should have this shape, a sequence of length 2 and a cycle, and with a labeling that respects the order on both alpha and beta. Respect the orders on alpha and beta. Okay, so if you do the product of these two guys, so you get a set of pairs, and for instance you have so you have to distribute the element 1, 2, 3, 4, 5 in the circles here in such a way that I respect the order here and here. So for instance I can put 3, 5 here, and here 1, 2, 4. Okay, so and it's easy to count the number of elements there because once I have choose once the elements are chosen 3 and 5, everything is fixed. So I just have to choose 2 elements in the 5 possible labels, and so what we get is so A star B, this is a label product B, is just the union of all alpha product beta. And you get that if C equals A labeled product B, then Cn equals, well, you split in two, and you get, and here you have An, Ak, Bn minus K, but also, so this is a number of possibilities, and also you have this binomial coming from here. Okay, and so if I expand this, I get that Cn over factorial n equals and this is why exponential generating series are the good notion for labeled structures, because we get that the exponential power series of C equals the product of the exponential power series. Okay. And we have more. If so, I will just write it, but the sequences still works. So if C equals sequence of A, then C of Z equals 1 over 1 AZ, but you have a lot more. For instance, you have cycles. So you put elements of A into a cycles, and the size is the number of atoms. Then C equals the logarithm of 1 over 1 minus A. And if you take a set of elements, then the exponential generating series of C is just the exponential of A of Z. Okay, so you take a set of something, a sequence of something, a union, and so on. You directly get the series. So quickly, okay, I will just make one example because I'm running out of time. So if you look at derangement, which are permutations without fixed points, then, okay, if you remember my drawing with the cycles, you have a fixed point when you have something like that, right? Okay, so I want to prevent this. And to do that, I first observe that a permutation is a set of cycles of some atom. So see, that is just one atom. Okay. A permutation of a set of cycles, and if I use my construction, I have it is exponential of logarithm of y over y minus and 1 minus z, and this is the exponential generating series of permutation, of course. And if you want to do the arrangement, Well, you want a set of cycles of length at least 2. You don't want cycle of length 1. Okay. So when I go to generating series, set is exponential. All cycle is logarithm of 1 over 1 minus z, and I remove z because these are cycle of length 1. Okay? And so you get that d of z equals exponential minus z over 1 minus z. Okay? And I have a lot of examples like this, but I don't have time, sorry. Okay, so I will just show you quickly one of those analytic theorems. Because the goal is to obtain some asymptotic equivalence. So here, I just give you some tools to directly build some generating series, and now I want to get some asymptotic equivalence to the coefficients. Okay, so consider this simple rational function if I want to know the asymptotic equivalent of the coefficients, one thing you can do is to decompose this function. I don't know the term in English, but you know that you can always write it this way. Right? And each such term, you know the expansion, because it's easy to compute that if you get something like 1 over cz to the k, then the coefficient is n plus k minus 1, k minus 1, c to the n. Okay, this is easy to compute. So if I have this formula and the decomposition, then I can compute exactly the coefficient of f of z. I have to compute alpha, beta, gamma, delta. And then I can use this to get every term. I sum all the terms, and then I compute the asymptotic equivalent. Okay, but wait. Maybe I can compute the asymptotic equivalent directly without computing everything here. And if I look at this formula, I will have something like c to the n when I have a c here. So this gives me a 1 to the n, a 2 to the n, a 2 to the n. This is polynomial, right? And this is a 3 to the n. So I don't need this one if I want to compute the asymptotic equivalent. This is the only one which is meaningful, right? This is the important one. And if I had something like y minus 3z to the 4, this is, you know, if you are, maybe I can write it, it will be easier. Okay, the only important term is the one with the largest c here and the largest exponent here. Okay, so I don't need to compute everything. I just need to compute this term. And the idea here is that if you look at f of z near this pole, where in 1/3, when there is something important for for us, well, it is equivalent to, you have this term in y minus 3z, and the rest is just putting 1/3 instead of z. Okay, which is, if I remember well, something like that. Okay, and you don't need anything else. So you just have to look at what happens when you cancel this one. So for z equals 1/3, and it tells you everything you need to compute the asymptotic, the first order asymptotic. Okay, so okay, that's cool, but it's only for rational functions, right? Okay, but remember my trees? I have t of z, I have an equation for t of z, and if I solve the equation, I have something like that. Okay? This is not a real pole in 0 because it simplifies, so you can remove the singularity here. And okay, what I want to say is that I'm starting to have a problem in 1/4, okay? Because this is 0, square root of 0, and I stop being defined or continue, or you cannot derivate or something like that, okay? Differentiate. So I want to look at what's happened the same way. Let me put it this way. If you start at 0 and go positively, the first problem you encounter is here, when z equals 1/3. And here, this is a false singularity, so the first problem you encounter is here, when z equals 1/4. And when z equals 1/4, you have, okay, so you have one term here, which is 2, I think. You have something like that. Plus some negligible terms. And let's focus on this one. So I'm going to say that this is minus 2 over 1 minus 4z to the minus 1/2. It's a bit complicated, but it's just to have the same kind of formula. Okay? And then, it's incorrect, but I will apply this equivalent. Okay? I have no mathematical reason to say it's correct, but let's try. Okay? So, I put some mark here. So, let's try it. So it's n to the k minus 1. So for me it's 3/2. Here it's k minus 1 factorial, so if I apply it with k equals minus 1/2, I use a gamma function because I need some kind of factorial over the rational. And c is 4 to the n, right? And I have my minus 2 here. And gamma, this, I need another color. E. This equals minus 2 square root of pi. And so you don't get, but if you simplify, you get 4 to the n to square root of pi n cube. And in fact, this is correct. The equivalent is correct. This is not correct, of course, because I just plug in the value in the formula, but the equivalent is correct. And so the idea is that we have a theorem, this is this transfer theorem, that tells us that the conclusion is correct. And so the transfer theorem is the following. If f of z is delta of rho analytic, I tell you what it means. It's an analyticity condition just after. And f of z when z is near this singularity rho equals, I just don't want to, 1 minus z over rho to z minus alpha, where alpha is real but not a negative integer. If it's a negative integer, it's just a polynomial here, so it doesn't work. Then this formula is correct. Okay. So this is non-trivial. It's not the same as just making the decomposition and identifying what is good, what is the most important contribution. So first, what is delta rho analytic? So now we are switching to complex analysis. This time, right? Okay. And it's just that your function, so I will be very quick. So you have the circle rho here. And you want it to be analytic in something a bit smaller than, a bit larger than the circle. So you have some angle here, phi. And you have to be able to expand inside this line. Okay. So here you have to be analytic. And so you have a problem here, a singularity here. And to prove the theorem, you use the fact that if... No, I don't have time, I think. Okay, to prove the theorem, I just write it, but I cannot explain it. You use the fact that your coefficient can be written by the residue theorem as an integral of a contour inside this of f of z to z minus l. Okay. Do I have 1 minute for the conclusion? Yes. Okay, so there are many other theorems coming from complex analysis that we can use here, and the main idea is the following. So if you have a combinatorial specification, the usual way to obtain the coefficient is to do some recurrences, then to compute closed formula, and then to obtain the asymptotic equivalent. And what we are doing is to go to generating series and then directly here using, so this is the symbolic method, and this is complex analysis. And also you can, if you have a recurrence, you can try to do this way. Okay, I will stop here.